Hello, my name is Hanzhang Wang, an applied researcher of eBay. This video is to present you a joint research effort between Fudan University and eBay around graph-based trace analysis for microservice architecture understanding and problem diagnosis. In this work, we took a graph-based approach to process, storage, analysis, tracing data, and built multi-layer and multi-purpose access APIs, and provided use cases around architecture understanding and issue diagnosis. Here's the agenda of this presentation. We will go over the background, problem statement, related work, then start approach introduction. Approach is divided into two parts. The first part is GMTA, which aggregates, analysis, and stores the trace data, at the same time provide accurate interfaces. The GMTA Explorer implements the trace data in visualization, comparison, and used for different scenarios. We will also introduce their validation respectively. At last is the future work and conclusion. As a popular development methodology, microservices become the default choice for building large-scale systems. Different from traditional monolithic apps, thanks to the loose coupling, the microservice architecture can be easily maintained and tested, as well as deployed independently. The deployment around business capabilities and small teams are also easier. As shown in the figure on the right, multiple independent services call each other to support the business together. Overall, microservice architecture can achieve faster velocity and transparency. These advantages have attracted many companies to adopt. But there's no silver bullet. It has its own issues, such as one service can still grow into monolithic one, or the ecosystem is hard to manage or can be grown out of control. In our work, the main challenge is around the observability. So the large number of the service and frequent calls between them can easily make it very difficult to monitor or localize the faults. And the data in a single system can be scattered around different instances or machines, which also bring challenges. So talking about the observability, the main three pillars are metrics, logging, and tracing at the basic, and they are often used to generate alerts or help with localizing the issue. There are many related tools and researchers for logging and metrics, but the industry currently use less trace data, and it is relatively a new area to explore. Our research mainly focuses on tracing in this work. So what is the tracing? The picture on the right shows a common single traces views. We know that in a microservice system, a request may pass through several services. In the upper left corner, you can see there's a user request passes through 3 services. The view in the upper right corner shows the sequence of the service invocation. The view in the lower left corner shows the start time and the total time consuming information of the service invocations. We take the information of each service invocation as a span and form a directed acyclic graph in order to understand the whole trace. Through this single trace views, developer and operation people can maintain and view the dependency between the services or analyze the performance issues. It seems that with these trace views, the problem of architecture understanding and fault diagnosis can be resolved. However, it is not the case. The main challenge comes from the growing scale of the microservice system. There's a huge amount of data, making it very hard to process and analyze the traces in real time. And there's also some quality issue. And given the scale, for example, eBay, it's very hard to look at the single trace to diagnose the issue. For example, in our system, there are over 3,000 services, over 10,000 operations. There's 800 billion spans and 147 billion traces per day. Even after 1% sampling, is still a relatively large number. So the problem derived into 3 main things. One is that it is very hard to understand the architecture and the business. Secondly, single trace is not easy or cannot be used for some diagnosis. At the end, it's very hard to localize the root cause during an incident triaging because you may start with a business metrics or a business issue, and then when you try to localize the issue, you cannot easily find a useful trace throughout multiple different passes or different spans traces. When it comes to tracing, Dapper must be mentioned. It's a distributed tracing system published by Google in 2010. Although there was a concept of distributed tracing before, the paper systematically organizes and introduced related concept for the first time. Dapper also providing a low-cost, low-latency, low-intrusive industry solution and a case. There are many solutions in the open source system nowadays, such as Zipkin, Jaeger, Pinpoint, Skywalking, and this open source distributed tracing system have all supported or using open tracing specification. Open tracing is a set of API spec and a collection of a framework libraries that implements this specification. Distributed tracing system that support open tracing will use the same data structure. Therefore, the trace data of these common tools are basically similar to single trace we introduced above. Open tracing not only allowed the manufacturers to unbind the specific tool, but also provide convenience for academic research. Our work used the trace data that conforms to the open tracing specification. The recent open telemetric integrates open tracing and open consensus and added additional capabilities which provides a unified specification of metrics on basis of open tracing. Many tools have begun to support open telemetry, which provides more possibilities for the future work. In addition to these individual trace tools and specifications, there are also some related research work around the tracing. Canopy is an end-to-end trace analysis system that's published by Facebook in 2017. It realizes the generalization and collection of traces like common distributed system, and on this basis, Canopy aggregates and summarizes the trace data, introduce a feature extraction during the aggregation analysis to assist in solving performance issues. Although Canopy did a simple aggregation of the trace, it did not explore more use cases such as path comparison or localizing the issues. The second paper proposes a new approach which used to compare trace-based request flow to find performance problem caused by changes. And the third paper proposed a method of failure management and evolution based on the path, which shows that the path can be used to narrow down the scope of the fault diagnosis. The method of the later two works are very thoughtful, but not related or very difficult to be implemented at a large scale or implemented for a large scale trace system. Our work uses trace aggregation, flow comparison, path-based analysis, and more ideas, and furthermore process the graph-based trace data, and added the business correlation, combined the error chain analysis, and other methods to have a end-to-end trace analysis system as well, so that we are able to do more useful scenarios such as path-based analysis, comparison of flow for the large system in the real time. Here is the high-level approach overview. As shown in the figure, our approach is divided into two parts. In the first part, GMTA process and stores trace data. In the first part, GMTA processes and stores the trace data. In this process, GMTA assembled, repaired, and aggregated the trace data, also recorded the error propagation chain information. GMTA adopts a storage structure that combines analysis database and graph database, and provided a multi-level query interface to solve the problem of poor query performance and poor data quality in the case of large amount of data. The second part, GMTA explorers provide visualization, comparison views, and error chain views to solve different particular problems, such as understanding the business, understanding the root cause, and localize it. Let's take a look at the conceptual diagram and system overview of GMTA. The above conceptual model introduces some terms involved in the GMTA. Among the concepts of service, operation, trace, and spine are recognized or have been introduced earlier. There are 4 more concepts on the right that proposed in this article. Traces have past, service, and operation are exactly same, and in the same order will be aggregated to the path. A path collected different traces that are passing through the exact same operation or services in the same order. The span in the trace aggregates and corresponds to the hop of the path. After aggregated into a path meets specific conditions will be grouped into business flow. In addition, the EP chain represents error propagation chain, which collects a series of error chain whose have the same calling sequence. The following figure shows the architecture of GMTA. GMTA is divided into 3 modules: processing module, storage module, and access module. After the trace is aggregated and analyzed, the span data will be stored in an analytical database, and the aggregated results will be stored in the graph database. The access layer combines 2 databases to provide a multi-level and efficient query interface. Let's introduce the details of 3 modules of GMTA in turn. The data process module of GMTA mainly introduces 3 parts: trace assembling, error chain identification, path aggregation, and business flow filtering. Taking this picture as example, in this example, the blue arrows spans are exactly the same, so they aggregated into the hops, and at the same time, the whole trace aggregated into the path. So you can see the red arrows are representing one same path of traces. And another example of the path is the green arrow. So the green arrow shows another path which passes through the user checkout flow. And the green and red passes can be aggregated by specifying the checkout service, and then they can aggregate it into a business flow called checkout. So this can be the checkout flow. This shows how we calculate the path ID. The trace with the same path ID will be aggregated into a path. So we have the service name and the operation name and the span levels multiply a prime number. The sum of all three of these will become a hash, and we recursively add for each child of the span so that we can get a unique number or path ID to distinguish this path from the other ones. Business flow can be defined by a series of service name and service operation. The trace that passes this operation or services can be collected and aggregated into business flow. We can also specify the invocation order to make sure we collect the right traces. Here is the data storage module. GMTA uses two types of database: analytical database and graph databases. Analytical databases can aggregate the data in column and provide efficient aggregation query from massive data. The graph database stores the data in a graph structure and can support graph-based related queries, but its performance is poor when the data amount is large. GMTA uses a combination of two. The picture shows the data schema of both. You can see the graph structure at the above. The circle is a service, the square is one operation, and then they have been connected by hop edges or service of edges. On each node or passes, there's some data being captured in there, such as service name, operation name. For hops, there's path ID, count, error count, and other details. At the analytic DB, we have stored raw spans with all the raw data available. At the same time, we also store the business flow mapping table. When a business flow is generated from the graph, we will keep a backup at here for easier access at the next time. With the pre-processing and separate storage of the trace data, GMTA can provide multiple levels of efficient query interfaces at the access layer. The trace level can provide a query interface similar to the current common distributed tracing system, such as querying a trace that meets the specific conditions. The path level can support query related to the path data after the aggregation and error propagation chain, and the return the results include some common aggregation indicators, such as average time, consumption, error rate, and so on. Business flow level can provide business flow generation and query interface. After implementing GMTA, we conduct two experiments on eBay dataset to verify the efficiency and effectiveness of GMTA. As shown in the table above, we have set 3 experimental systems for comparison. Among them, OTDR is a common solution adopted by most tracing systems and only supports the trace level queries. ATDR is a solution previously implemented at eBay, which aggregates traces into passes, but does not use graph-based storage, nor does it implement business flow filtering. The last system is the GMTA that we have introduced. Then we designed 6 common use cases. For the result, it can be seen that compared to OTDR and ATDR, our approach can support queries for more scenarios, while GMTA also have better performance. GMTA approach also achieve better efficiency. We have conducted 2 experiments to prove that. On the left is a trial for collect metrics of a given operation with a certain condition. For the code data, we have around 65% of improvement, and for the hot data, we have 24% of the improvements. When constructing and returning a business flow, comparing to the ATDR approach, which is the only one that's supported for this kind of action, the query performance of GMTA achieves various improvements and significant improvements as well. After we build the GMTA system, it's time to introduce the GMTA Explorer, which uses the query interface to provide different functions. This table shows 4 main functions of GMTA Explorer and how they are using different data. We have basic visualizations that can view a trace path and business flow. At the same time, we can detect the change and present it. Also, there's anomaly comparison where we aggregate different passes, business flows, and show the error propagation chain. And we can also query a particular error chain by giving operation or a service name. The first use case that GMTA supports is architecture understanding. There are 2 examples we give here, and they are the mocked UI. The left picture shows the basic visualization functions of GMTA Explorer. The squares in the picture represents operations. Operation with the same color belongs to the same service. GMTA Explorer can provide 3 levels of visualization: business flow, path, and trace. The business flow in the figure have 3 different passes. expand the third pass into the two traces at the bottom. The picture on the right shows a comparison view of the business flow. In this picture, the square still represents operation, but the color represents the change of one matrix that belongs to this operation. Red means it's being reduced comparing to the past, and green means it's getting improved or better than the past. We can see there are three passes have different colors, and this can represent different scenarios. When we merge all the passes, we can have a different view, where in this example, you can see the coupon is getting expired or disabled, and a new version of the code has rolled out. In this case, the developers can use it to understand the architecture change or the impact they are making to the whole ecosystem when they're deploying or introducing a change. This is an example of using GMTA for problem diagnosis. In this example, we can see the coupon function experiencing a high error count. However, it is what we call soft error. It doesn't cause any production issue, so we don't need to be paying attention to these issues. However, the create order services is experiencing a critical error. We know this by comparing the history and the recent behavior of each services or operations metrics. We notice that this have a spike from 0 to 10, and also its downstream operations having the same spec, and this arrow pass is aggregated as EP chain. So when we're doing the Explorer view for problem diagnosis, we can show the arrow chain views that aggregates the issues such as create order, update inventory, and verify inventory, this chain. And this will pops out instead of showing all different arrows happened at the time. And the SRE or developers can easily find which is the new issues that occurred to help them find the root cause of a potential problem. We have conducted a case study for GMTA Explorer. We have interviewed 20 team members. 7 of them are developers, 10 of them are site reliability engineers, and 3 architects. Most of the people believe that GMTA Explorer can help with understanding the architecture as well as using the EP chains or the aggregated view to help with the problem diagnosis. We have listed a couple case studies that collected from the interview. We just give 2 brief examples. And this is to support architecture understanding. We mock the UI again using Jaeger and hided the API names. In this example, the developer wrote out a new code and wondering the change and impacts to the downstream services. He couldn't know this easily by using any of the existing tool. However, when he tries the GMTA Explorer, he can clearly see that his changes enabled a new pass and completely disabled another pass of the services. Some of these services belongs to the other team. So in this case, he saved a lot of time to communicate with other team or to understand this himself. The last example is for problem diagnosis. This is collected from a site reliability engineering doing his on-call. There was one service marking down a downstream service, and there were over hundreds dependencies for 2 steps. So it was really hard to find who is the root cause, because they noticed the root cause wasn't on this service B. When they tried the GMTA Explorer, we show them exactly this arrow path where there's an arrow chain floating on the B, D, and BC. So they can click and jump into the dashboards we built, and they notice that there's a significant dip in TPS, spike in latency. Also, the success rate has been dropped. For another operation, it has a spike of TPS, and then the latency were very unstable. So this shows the issue or the root cause is on the service C. It turns out it's caused by a code deployment. As for the future work, we plan to add more query interfaces to support different use case scenarios. We're still exploring other use cases, and we also plan to explore different usage that can be implemented in the industry. And also, we are trying to combine the work with the existing AI ops efforts, where we can leverage lots of detection models and localize the issue at the trace level. As a conclusion, in order to resolve the high volume and the quality issues of the trace, we implement GMTA and use a graph-based principle. We process the trace data, recover it, and aggregate it into paths, then split it into business flows. Also, to help with discovering the error propagation chain, we use analytical database and graph database. We also implement GMTA Explorer to help with the use scenarios such as visualization comparison, error propagation comparison, and business. We also implemented GMTA Explorer, which can help to understand the architecture, support for diagnosing different issues, and as well as localizing the root cause. Thank you very much.